Hello everyone, I'm Dhananjaya Wijerathne from National University of Singapore. So today's talk is about accelerating edge AI with Morpher. Morpher is an integrated design, compilation, and simulation framework for CGRAs. So this framework has been developed in collaboration with my colleagues in National University of Singapore. So there are mainly two kinds of accelerators, domain-specific accelerators and reconfigurable accelerators. In domain-specific accelerators for domains like video, ML, or audio, for each domain, there's a separate accelerator that can accelerate kernels from each domain. So for example, Apple iPhone's 12's A14 Bionic SoC consists of multiple accelerators, including HDR video processor, a machine learning accelerator, and a high efficiency audio processor for each of these domains. So even though these kind of mobile SoCs can afford to have multiple accelerators within the same SoC, tiny IoT devices which have ultra low area and power footprint requirement cannot afford to have multiple accelerators on the same SoC. So as a promising alternative, we can consider the reconfigurable accelerators. So most well-known reconfigurable accelerator is FPGA, which offers bit-level reconfigurability. In comparison, the coarse-grain reconfigurable arrays or CGRAs offers word-level reconfigurability, which is much power-efficient alternative than FPGAs. So to give more context about CGRA acceleration, so I have an application or tiny ML application, which basically recognize speech commands like yes and no. So in this application, we have multiple components. Basically, the input is taken from device microphone, and audio provider captures audio and samples from the microphone, and feature provider basically convert this raw audio into spectrograms, and spectrogram is fed into machine learning model, which act as a classifier to classify the speech commands, and the speech recognizer following the speech responder basically takes action based on which command was heard. So if you look at main application kernels that takes um, computing time, basically feature provider runs FFT kernel, and this ML model runs fully connected or general matrix multiplication kernel, and the convolution kernel in the convolution layer. So all these layers or all these kernels can be accelerated on CGRA, because CGRA can basically support different data flows by reconfiguring its interconnect at runtime at each cycle. So if we look at the CGRA architecture, so CGRA architecture is a power efficient mesh of processing elements, where each processing element consists of an ALU, register files, switches, and also the configuration memory, and also data memory that is connected to subset of processing elements. So CGRA basically gets its flexibility through its execution model. So it basically runs through a schedule and configurations, which is compiler generated and adapted into a different application kernel mapped onto CGRA. These execution schedule or the configurations are kept in the configuration memory, and at runtime these configurations are cycled through to repeatedly execute those instructions. So there are many commercial CGRAs that is already available, like Sambanova and Samsung reconfigurable processor. If you have a Samsung phone, probably this SRP processor is in your phone as well. And Renesas as well as Wave GPU, all kind of the commercial CGRAs that is already available. And in academia, especially in NUS, we have already fabricated two CGRA chips, HighCube chip on 2019. And Pace chip is we recently fabricated this CGRA accelerator. So I will go into a bit more details about these accelerators. So in HighCube, CGRA, we fabricated it in 2019 in our group in NUS. So it is a 4x4 CGRA, which can reach 19 MOPS per milliwatt, power efficiency. And recently, we fabricated a bigger version of the chip, 8 by 8 CGRA, and this CGRA chip basically cross like coupled with a RISC-V CPU, host CPU, and it is able to reach 582 gigahertz per watt at 40 nanometer, and it is estimated to have 1 teraops per watt at 20 nanometer technology. So this is the CGRA SoC as well as the development board that we have developed in NUS. So this PACE CGRA SoC was developed in collaboration with NUS as well as Institute of Microelectronics. As I mentioned, it has a CGR accelerator coupled with RISC-V CPU. So we have developed, so I'm not going into the details of the CGR accelerator, but the main focal point of this talk is about the toolchain, how we developed the end-to-end compiler, which can map applications onto this PACE CGRA chip. So basically, this MLIR-based end-to-end compiler, actually, this one is ongoing work where we try to do end-to-end compilation from higher level ML model like PyTorch or TensorFlow, written into PyTorch or TensorFlow, and leveraging the MLIR framework in order to map those the kernels from these high-level models into the CGRA. So main discussion about in this talk is about the Morpher toolchain, which we have already developed. This Morpher toolchain is basically taking loop kernel as an input, either from LLVMIR or as a C program, and it can basically map those application kernels onto a user-given CGRA architecture. So this toolchain is not just limited to PACE CGRA, but it can be used as an architecture explorations tool, because we provide architecture abstraction model or architecture abstraction language, which can use by any developer. So I will go into the more details in the next slide. So before going into the details of the toolchain, let me give a bit more context, a bit more background about the CGRA application mapping process. So as CGRA repeatedly cycle through a small set of configurations, application loop kernels are the perfect candidates for acceleration. So CGRA compiler first extract the data flow graph or DFG of the kernel, where nodes represent operations and edges represent the dependencies between these operations. So then the compiler maps DFG onto the CGRA processing elements. The mapping process consists of placement and routing step, where DFG operations are assigned or placed onto ALU in functional units, and the data dependencies are routed using wires and registers. So CGRA compilers exploit inter-iteration parallelism using software pipeline techniques. The goal of the CGRA compiler is to obtain an optimal schedule with minimum initiation interval. So the initiation interval is the II, or the II is the cycle difference between initiation of two consecutive loop iteration. Therefore, lower the initiation interval, higher the performance. So going back to our toolchain, so it is an compilation and simulation framework for CGRA, as I mentioned. So as I mentioned, we provide flexible architecture specification language, which the user can express their own architecture using this language. And we provide efficient mapping algorithms, and we are not just limited to map simple loop kernels or toy kernels, but we allow the loop kernels to have a control divergence and also the recurrence edges. So the tool also generates RTL automatically from this abstract architecture model, and we provide cycle accurate simulation using Wijerathne. And most importantly, it is fully open source. You can locate the locate the repository of the toolchain using this QR. So I will give basic introduction about each of these components in the toolchain before going into the details of the machine learning kernel mapping. There are three main inputs, as I mentioned. So the first one is the application source code annotated with annotated kernel. Here we have loop kernel, which basically adds two arrays and store in another array. So basically, we use this annotation string in Morpher to annotate which kernel is the target loop kernel, to mark the target loop kernel. So the other two inputs are the abstract architecture model. So we have developed an architecture description language based on JSON, where the users can simply use a set of basic express the connection between the basic modules like ALU, register file, and switches in order to to design their own architecture, and also to connect those processing elements in a way that user wants to. And also we provide the detailed implementation of each of these basic modules like ALU and switches. So this basic implementation is provided in Chisel as a library, and users, if they wish to add more complicated or more optimized version of the basic modules, they can also add those implementations written in Chisel. So based on these three inputs, there are multiple intermediate data that is generated by the toolchains. The first one is the data flow graph generator generates a data flow graph of the loop kernel. So it is a LLVM based DFT generation tool, and also it generates SPM data layout by assigning the array and live in and live out variables that into the CGRA local memory. And CGRA mapper basically takes the abstract architecture model and data flow graph as well as data layout as input, and generates the mapping configurations by mapping the data flow graph onto CGRA on a spatiotemporal manner. So the architecture generator tool also takes the chisel modules as well as this abstract architecture model as an input, and automatically generate the Verilog RTL. And also our toolchain, we have a data generator which can automatically extract test data for verifying the execution. So basically it captures live in and live out data. Live in data means the data that goes into the CGRA before execution, and live out data is the expected results. So using these three inputs, basically we have a validator based simulation as well as C++ simulation only for high cube chip. So the validator simulation takes mapping configuration test data, and also the Verilog RTL, and do the verification. And we provide waveform based simulations as well as command line based verification results after this execution. I will skip this artifact demonstration. You can find this artifact demonstration from the GitHub repository that I have already mentioned. So in the experimental study, we are showing in this work how ML workloads can be mapped onto user given CGRA. So in this experimental study, we are using an 8x8 P array with 8 data memories on boundary P's. So this basically the CGRA is logically arranged to uh, 4 for like 4 clusters. So where each cluster has a 4x4 P array and 8 kilobyte data memory. Each of them are connected to 2 P processing elements. So the kernels that we are mapping in this experimental study is GMM, or General Matrix Multiplication kernel, and convolution kernels, which is widely used in most of the machine learning models. So the dimensions of the GMM and convolutions are given in this as in the slide, and also the tile size are like this. So if you look at in the GMM mapping, so GMM computation, we have W matrix and I matrix here, and give the output matrix. So based on the available memory on chip memory, so we need to tile the GMM computation onto multiple tiles. In this case, we have 8 output tiles, where each tile is mapped onto one CGRA cluster. So since we have 4 CGRA clusters, we can parallelly operate on 4 CGRA tiles, and we need only 2 invocations to complete the whole computation when we have this kind of tile configuration. So this is just one tile configuration that we have manually written. There could be many other tiling configurations that can be applied onto GMM computation. So the similarly convolution mapping for convolution mapping, so we have considered a single input channel input channel and multiple output channels, where we have multiple weight kernels as well. So in this case, we have assigned each output kernel into a single CGRA cluster. So each single CGRA cluster basically operate on a single output channel. So this is also based on the memory requirement, memory availability on the CGRA. So even this is also as one single instance of multiple possible tiling configurations that can be basically basically this is just one instance of multiple such tiling strategies. So the main focus of this work is to how do we map each of these kernels onto one CGRA cluster. So if we have a GMM kernel, so this is a GMM kernel in its original form. We have three for loops where so in the first figure we can annotate the inner loop to map on the CGRA. So if you do that, we get 26 instructions in the inner loop, and the P utilization after mapping this loop into the CGR is 14%, 40% P utilization, and number of inner loop invocations in this case is the multiplication of the outer loop number of outer loop iterations. So in this case, it is 4096. So these multiple inner loop invocations basically leads to so the CGRA host needs to send multiple control signals in order to invocate the loop invocation. So there will be multiple more data transfers if we have multiple the more invocations you have, the more data transfer that you need. So the goal of the microkernel mapping is to try to reduce these invocations, as well as try to utilize your CGRA PRA as much as possible to get the maximum benefit of the acceleration. So in the second example, we have unrolled kernel. We have unrolled the inner loop of the kernel 4 times. In that case, we get 58 GFG nodes, where we have a bigger DFG now, and from that we can get a 60% P utilization, but the number of invocations is same as in the previous case, because we have the same number of loop levels. So in order to get rid of these inner loop invocations, we can use loop coalescing optimization. So in this the final example, we have coalesced the loop by basically converting these 3 loops into one loop by introducing these if else or control flow statement into the inner loop body. So since Morpher toolchain can map these kind of complex loop kernels with control for statements within the loop body. It can support this kind of optimizations. And the number of DFT nodes in this case is 79. The P utilization is roughly the same, but we can reduce the number of loop invocations to one, by which gives huge speed ups uh, because of the less invocation overhead associated. So similar, so this is the convolution kernel mapping. So we can apply the same unrolling and coalescing techniques into convolution as well. So by unrolling, basically we can increase the PE utilization by 52%, but finally after coalescing, this coalesced loop basically gives 86% PE utilization, and most importantly, number of inner loop invocations are significantly reduced by coalescing, because convolution loop kernel has a 5 loop level. So by removing all those 5 loops and creating one loop, basically reduce the inner loop invocations significantly. So you can see these in terms of the results. So as I mentioned, the GMM unrolled and coalesced kernel, we get 3.5x times performance speed up compared to the original GMM kernel. And for convolution, this speed up is very significant. It's 25 times speed up compared to the original kernel, because this is mainly because we can reduce the data transfer time because of the significant reduction of the number of loop invocations. So that is the conclusion of our talk. So basically, you can also use our CGRA compilation and simulation framework to model your CGRA, your own CGRA architectures, and map complex workloads. So we have given just 2 examples kernels, but you can try your own kernels using our toolchain. So we can also you can automatically generate the RTL, and we provide the cycle accurate simulation to validate the compilation results. So the tool is fully open source and it's modular. So I hope you can also contribute to the tool. So if you are interested, you can contact us for contributions as well. So you can find the tool by scanning this QR code, and I hope you enjoy and you can use this tool for your research as well. So, so that's the end of my talk. Thank you very much for listening. And if you have any questions, you can ask them now.